and welcome. This is the end of course review for Chapter 5, and we have a lot to cover. Chapter 5 has exponential growth, exponential decay, compound interest, and logarithms. So there is a lot in this chapter. Let me remind you that the formulas that are given to you on your formula sheet are exponential growth, which is when you have a base that is greater than 1. You can tell right here in this formula, you are adding something to 1. So if you see a formula that has like 10 and then 1.8 to the power of t, then that is going to definitely be a growth, and it is going to grow by 0.8 or 80% growth. Decay is going to be something that is between 0 and 1. You're going to be lucky if they tell you if it's 1 minus 0.2, but if it's 1 minus 0.2 and they don't write it that way, they could say 0.8 instead. So you have to think 1 minus what number is going to give you 0.8? Well, that happens to be 0.2. So your loss or your decay rate would be 20% in that case. Compounded interest, make sure that you understand that compounded is going to be n times a year. So that could be 365 days a year. It could be quarterly, which is 4 times a year. It could be weekly, which is 52 times a year. If they decide to go with continually compounding interest, you're going to use this formula. It's a completely different formula for that. Okay, so this is the relationship of the inverse and the original function. We talked about that in Chapter 4b. You notice how the logarithm here is growing. That is going to be the inverse of a growth that is exponential. So you can see the difference. You've got an exponential growth base 3, but a logarithmic growth will also have a base 3 as well. This is exponential decay, which is the blue line, and logarithmic decay, which is the red line. They will have the same base as well. Over here, we talk about how we have an asymptote with exponential growth or decay that it's going to start with the x-axis, and unless you are making it translate up or down, it's going to be both x-axis for a growth or a decay. Now let's talk about logarithms for a second. So logarithms will have 2 different types of logarithms. You have a log logarithm. If you don't see the base, that is considered a common logarithm with base 10. Or you can have ln with an invisible base, which is base e. Unless it's base e, everything else is going to be an log style logarithm. The good news is all your transformations are going to be the same as they were in chapters 1, 2, 3, and 4. And you need to be a pro at changing a logarithm to an exponent and then going back from an exponent to a logarithm. If you are in honors because I don't think I taught this to my regular classes. I don't remember. But what we're going to do here is, if you notice that we have the same base here, you can drop those bases and make those exponents equal to each other and solve it like a normal equation. If they are not automatically the same, you can make one of those bases the same, but you will have to change the exponent on that particular base. All right, this one, if you have a base of 2, when you go from logarithmic to exponential form, you are going to start with the base. It doesn't matter if the base is on the left side or the right side, whether it's a logarithm or an exponent, always start with the base. So you're going to start with base 2, then you're going to make a circular motion to the other side of the equation, power 8, and then circle back. That's going to equal to 256. So a logarithm is just another way of writing an exponent. So if you get stuck solving a logarithm, you typically need to change it to an exponent. If you get stuck trying to solve an exponential function, you're going to probably need to change it to a logarithmic form. And I think the last thing we need to talk about before we do the examples on the back is exponential regression. I think there is a high chance or high probability they will ask you either a linear regression, a quadratic regression, or an exponential regression. This is the code that you're going to type into Desmos. Just type in y equals a b to the power of x, and then make your 2 changes. Put 1s next to x and y, and then change equals to a tilde. All right, we're ready to do some practice questions on the back of Chapter 5. This first one, we don't have access to a calculator. It's because we don't need one. Basically, it's just asking you which one has the greatest output whenever you have a large x value. That could be 100, it could be 1,000, it doesn't really matter. So, as a good Algebra 2 student, you need to be able to look at a function and tell me what kind of function it is. This is linear because it's x to the first power. It is also positive, so I know it's going to just kind of do this straight line pattern, but it's going to be an increased pattern. This is squared, so it is quadratic, which is kind of like a smiley face, parabola shape. That is going to grow faster than A, so I'm going to go ahead and mark out A. C is exponential because you have x in the exponent. That is going to be exponential growth. It is going to start growing and then grow faster and faster and faster. So the bigger x is, the faster it grows. I'm going to tell you right now, this one's going to win out because exponential functions are going to grow faster than any other type of function. This one, the last one here, is a cube root function, and that one's kind of a slow grower. It's going to be slower than all the other three. So the other three. So definitely win out with that exponential growth. And if you are comparing one exponential growth to another exponential growth, just pick the one that has the bigger base. Because if you have 2 to the power of x compared to 3 to the power of x, the one that is doubled is not going to grow as fast as the one that is tripled. So this one would win between the two of those. Okay, average rate of change, it keeps popping up from time to time. Average rate of change is another word for slope. It's just slope of a function that is not linear, so it could have a curve to it. So it's going to be the slope of 2 very specific points, and they're going to tell you month 1, month 4. So all you have to do is locate month 1 and locate month 4. If it is a graph, you need to find the x and the y coordinates. They have to give you your x coordinates because that's the interval provided to you. If it's a table, it's very easy. Just write down the coordinates. Look on your formula sheet for the slope formula and go ahead and plug it in. It'll be the y's minus the x value. So that gives you 111 over 3, which is going to simplify to it's going to simplify to 37. So this next one, it says using the exponential equation that best models the data. Model, line of best fit, those are going to be regressions. And the regression for an exponential function is y equals a b to the power of x. I'm going to show you how to do that. But first, what we need to do is go to Desmos, and we're going to type in our values here. And I have already done that for you. Obviously, I can't see them because these are very large numbers, so I'm going to click on this little magnifying glass to fit. It kind of looks like a straight line, but it is not a straight line. It is exponential. So I am going to type in y equals ab to the power of x. And what I have to do, that's going to give you that error message, which is normal. You have to put a 1 next to your y and your x. And then you still have an error message because that equals needs to change to a tilde. Okay, so yes, that has a slight curve to it. It's zoomed way in. If I zoom back out, I kind of want to, there we go. See, now you can see that growth. I'm going to zoom back in now. All right. So what I'm going to do is I'm going to use 2400 and I'm going to use 1.1 for my initial value here. No. Sorry, 2400 for your initial value, and your growth rate is about, I don't know, it looks about 12%, 11, 12%. So it wants me to predict for 10 years. So that means that x is going to be equal to 10. So when I say x is equal to 10, it should pop up. So the reason why I can't see x is equal to 10, if you look, I didn't have 10 on my zoom, so all you have to do is just change your zoom just a little bit. And then I'm going to, I'm going to go up here, do a little clickety click, and it should be around 7400, so it's got to be D. All right, this one looks kind of scary because we've got some kind of a Richter scale type formula that we use in the real world with earthquakes. So I'm just going to write it down, and then it tells me that I need to solve for n. And there's absolutely no way that I can do anything with this logarithm. I am stuck. So if you get stuck with this logarithm, you need to change it to an exponential form equation. So first thing you need to recognize is this log has a base of 10. If it's invisible, that's your base. Remember, always start with the base if you are converting. So I'm going to start with the number 10, and then I'm going to make a circular motion. That will be power r. See how it matches here and here? This, on the other hand, I'm a little wary of these two, but I think A and B are definite contenders here. And then it's going to be equal to n divided by 2. All right, so now I'm just kind of like at a pre-algebra question. Whoops. And I got to get rid of the 2. So divide by 2 means I have to multiply by 2. And the only one that says 2 times 10 is B. So that has to be the answer. Same thing with this one. It says the formula here, m equals log, and then it's got this ratio. I need to solve for that ratio, so I don't have to do anything fancy with that, but it does tell me that m is equal to 1. So I'm going to write down 1, because I just substituted the 1 for m, and then I'm going to put log of a over a 0. Now, remember, I am stuck. There's nothing I can do. So the first thing I'm going to write down is this little invisible 10, and I'm going to try to convert to an exponent. So it'll be 10 to the power of 1, circular motion, is equal to a over a 0. And guess what? That's all that we had to do. So it wasn't very scary. It wasn't very complicated. You just have to recognize that you have a log of base 10, and then you just change it to exponential form. All right, this one over here, hopefully it will actually be written out like this on your EOC, but there's no guarantees. If it looks like this, you know that it's going to be a growth because obviously you're adding something to 1. But they did separate it for you right here. You know that you are adding exactly 0.038. If that was a decay, you would probably have to figure that out on your own. You'd have to subtract it from 1 to see what you were losing. So since this is a growth, I'm going to immediately get rid of decreasing. And it's going to have to be either C or D. So 0.038. If you just move that 2 places, that is going to be 3.8%, not 38%. All right, this is a different style of transformation. They're giving you 2 functions, and then you have to figure out what's going on. There's lots of different ways that they can ask you about transformations. They could give you equations, they could give you words, and then you make the new equation. They could give you a table of values of x and y, and you have to figure out which one's changing, if it's the x or if it's the y, and how they're changing. So there's lots of different things that you could do with that. But right here for A, I can tell that we are adding 1, but we are adding 1 specifically to the x, which means that we are going to be moving left because it's opposite of what we think. It will be left 1. The only difference between F and G here is a little negative in front of the x. So if you have a negative, it's going to immediately reflect, but how? If the negative is with the x, it will reflect over your y-axis. If the negative is in front of the function, it will reflect over your x-axis. This one's a little bit tricky because you start with +4, but you wind out with nothing, okay? So that +4 turned into +0. So what are they doing from here to get to 0? They are moving it down 4 places. So they are subtracting 4 from the function. So in a couple of examples, we have converted logarithmic to exponential form, and in this one, we need to convert it to logarithmic form. You need to find the base in this problem. The base is 2. Start with the base. What's weird, though, is that you don't have log. If it's an e, I want you to use ln, okay, because a natural log. But if it's anything other than e, you're going to have to write down log. You're going to start with log, your base is 2, and then do circular motion. So 2 of 1/8 is equal to -3. That's it. This one is asking you about change of base. Change of base is handy if you have a yellow calculator because you can't type in log base 3 of 7 on your yellow calculator. If you have Desmos, you can type in log base 3 of 7, but you've got to remember how to do it. So if you don't remember how to do it, change of base will allow you to do this on the yellow calculator. Remember, start with the base. Always start with the base. So it'll be log of 3, and then it'll be log of 7. That you can type in your yellow calculator and you can figure out what it's equal to. And good luck on that quiz and good luck on the EOC.